Welcome to the first lecture in our winter lecture series, the noontime lecture series at Cal Poly Pomona. I just wanted to introduce our speaker today, Alvin Huang. People are already clapping. Alvin is the principal of synthesis design and architecture in Los Angeles and an assistant professor at the USC School of Architecture in Los Angeles as well. Alvin received his B.Arch from USC and his master's from the Architectural Association in London. Before moving back to the US, he worked in London in the offices of Zaha Hadid and for Future Systems as well. And I think probably in his work you'll see a pretty strong connection between their work also. He has also taught design studios and master classes at the Architectural Association, the University of Calgary, Tongji University in Shanghai, Tsinghua University in Beijing, University of Lund in Sweden, and Chelsea College of Art in London. His work has been widely published and exhibited and has gained international recognition, including being selected to represent the UK at the Beijing Biennale in 2008, along with numerous awards, including the 2014 ACSA New Faculty Teaching Award, the 2014 ACSA Faculty Design Award, 2014 AIA Small Projects Award. There's a lot of these awards. But most recently his firm won the 2014 AIA Next LA Award for the Daegu Gosan Public Library competition. And his firm is responsible for widely published pure tension pavilion design for Volvo, which is currently on a world tour featuring stops in China, Italy, and also Palm Springs. Beyond his professional work, he recently served as the conference chair for Acadia, an organization dealing with research, education, and computational design methods that impact creativity in the physical environment. And we are very happy to have Alvin here at Cal Poly. Please join me in welcoming him to our school.
Having me here. I'm a little bit embarrassed. I didn't expect to have the bio from my website read aloud today. This up. All right. Anyways, it's a pleasure to be here. I grew up went to high school not too far from here. I went to rolling. Went to Claremont High, so very familiar with the 909 and its many trials and tribulations. But very happy to be here. As Bob said, I teach at USC. I'm also an alumni from USC, and very happy to be back in Los Angeles after 9 years in London. And the weather is not too bad here. I have a small practice called Synthesis Design and Architecture. We're based in Los Angeles, and really interested in exploring what I like to talk about in this talk as coincidence, incidence, interference. And it's about moire patterns. And I want to talk about moire patterns not as something that is a literal representation of a moire, but a figural understanding of the moire. So if you're not familiar with a moire pattern, you start with a base pattern. You take a overlay, another pattern, and when those two patterns are laid over one another, you get a third pattern that emerges, a moire effect. And as I said, I'm very interested in this as a visual, kind of provocative thing about space and time and interaction, but also one about kind of figuratively understanding the relationship between design research and design practice. So what the moire pattern produces, I'm identifying as sort of three separate kind of areas of expression or articulation. Coincidence being when the two patterns align, incidence being when they intersect, and what I'm most interested in is interference, where the two patterns multiply. So the first two you can look at as kind of additive processes of understanding two patterns as 1 + 1 = 2, whereas the third one, you think of it as something that's exponential, like what you get back as that interference pattern is far, far, far more powerful or far more interesting than 1 + 1. And what you start to see is something that really shifts and changes as you move around it. And so where I'm interested in thinking about this is design practice being something as one pattern, design research as the other. And design practice, where we're really interested in technology as a tool, and technology is always kind of looked at as something that automates, that makes things more expedient, more efficient, things like BIM, which is very much about kind of production. And design research, where we're always looking at technology as something that is search for a technique, search for novelty, search for new ways of thinking. And where I'm interested is where those two kind of conditions overlap, this sort of condition where practice and research overlap to inform a new design intuition, an intuition that's kind of informed by a sensibility of understanding how these tools and these techniques operate and how we begin working with them the same way you historically have worked with things like paper and pen, card and paper. We're working at a number of different scales, from very, very large projects down to very small projects. Some of these projects are academic, some of them are self-initiated competitions. Been lucky enough to win a couple, gone through commissioned projects, been lucky enough to build some of these things. All of them are what we would call applied research projects, with 4 main topics of research. All of these topics are slightly different in each of the projects, and as you can see, there's a lot of overlaps. Some projects belong to many categories, some to one alone. The first topic I want to talk about is digital craft. And I don't like to talk about digital fabrication, I like to talk about digital craft. And when I say digital craft, it means that craft is now something that has extended out of the physical into the digital. So the notion of craft, as it is with the handmade, is that the person doing the work has an understanding, an intuition, an ability to understand the medium and feel the medium in a way that they were not able to without a previous knowledge of working with it. And so now when you think about craft, you're not only talking about the handcraft of sanding something, but you're also talking about the craft of modeling, the craft of understanding G-code, the craft of understanding what are the protocols for a file-to-factory process that sends a file to a CNC machine, and understanding how that CNC operates. This is a project which was a result of a competition which was won by myself and my colleague Alvin in London at the AA. It is a pavilion to celebrate the 10-year anniversary of the Design Research Laboratory at the AA. It was sponsored by a material manufacturer called Fiber C. Fiber C is a fiber reinforced concrete. So the site, as you see over there on the left, is Bedford Square in London. The entire project has to be manufactured from Fiber C, which is, as you see here, glass fiber that is spun and then thread as a matrix into concrete sheets. So essentially what it's making is reinforced concrete, but reinforced concrete without steel, with fiberglass. And because it's made with fiberglass, instead of making big slabs, you're making thin sheets. So thin sheets of concrete that are equivalent to plywood. We came up with a geometry which was a big continuous motion, which was really trying to house all of the different programmatic functions of the pavilion under one gesture, but have it switch from being enclosure to seating, to stage, to work surface, to roof, all in one move. And has to be made out of this flat material. And so we came up with this kind of grid shell technique, which was looking at tensioning the material into place, basically because it's a fiber reinforced concrete. We spoke with the manufacturers and they said that it could flex and lock into place, and we basically proposed that we would bend the sheets into place and lock them in, and they would actually hold in place by their friction. So the tension of the pieces trying to pop back out would lock them into place. We are working with, this is sort of pre-Grasshopper, so we are working in what we would call manual parametrics. It's parametric thinking or associative logic, but you're doing it by hand. And so you're basically looking at creating what I would call the sort of puppet master to control the puppet. And it's a series of rigging geometries which produce a successive series of geometries. And all of these, in the end, produced, at the time of the competition, we had, I think it was 2,000 unique intersections to resolve. Through the process, we got that down to 900 intersections, but rationalized into exactly 7 types. So from 2,000 details to solve, we've moved to 7. And all of those locking details are what we were looking at, you see here on the left. What our structural engineers were looking at, you see here on the right, which is they're only interested in the intersection, not in the locking. So they want a line node model, which basically tells us exactly what the line node network of those intersections are. They wrote a custom script in C#, which basically analyzed the dead loads on all of the geometries and how they were being distributed, and actually began to size the depths from our line node network. So what you see here is like a Gothic arch or a kind of traditional vault. You start to see that the forces get much larger as they get towards the noses. And as you can see from here, what started off as our very thin profiles start to get really deep. So we began working with this standalone plugin and beginning to kind of twist and manipulate the model to try and reduce the structural depth. In the end, we managed to get the structural depth down to a reasonable dimension, but we had to introduce a dirty little secret, which is what you see here, 3 steel continuous beams, which we painted gray and pretended they were concrete. But basically, when we managed to get all of the structural loads into order and the depth in order for the dead loads, what we were not able to achieve were the live loads. So the lateral forces of the wind blowing on the structure actually, we had issues with racking. And we went through a number of different iterations in terms of trying to figure out different options for how to reduce the racking. In the end, the most discreet one was to introduce this 3 steel beams and pretend that they didn't exist. We produced an 80-page construction document. We knew this is all going to be CNC milled water jet out of the fiber reinforced concrete panels. And so we knew that traditional plans, sections, elevations, blow-ups were not going to be able to describe the way we were going to construct this. So what we produced was an 80-page IKEA flat pack instruction manual. We basically spent a lot of time with IKEA manuals trying to look at how they describe things not as build-up, but as sequence. In the end, we had a script written which basically found all of the intersections in 3D space, sized their notches based off of their angles, named the intersections based off of the name of the profile and the name of the intersection, the name of the profile it was intersecting with, unrolled into 2D space, nested onto flat sheets, cut, and then ordered in reverse order of the sequence that we had placed them in our drawings. So this was an amazing script that I did not write. It was written by my friend Mark Fornes of the Very Many. And everything is water jet, delivered to site in the reverse order of the way it wants to be assembled, so that when you unpack it, it's in the correct sequence that you want to assemble. There's a little gap between this slide and that slide, and that is when we showed up to site with this truck with 800 unique profiles, we realized that they did not get us a parking permit. So they had to send the truck back. The next day, when the truck came back, we found out that overnight, this is London, our forklift was stolen. And we had a 2-hour parking permit to get 800 unique profiles off of this truck. So we went into the AA and we got every freaking student we could find to come out and throw all of those 800 profiles that were reverse order packed into about 35 random piles. We then spent 2 weeks trying to get a level site with student builders. After 2 weeks, we said, fuck it, let's just start. Went through the whole process of building up, managed to get everything built in time. Opening night of the pavilion, using mostly this as we ended up giving up on our 80-page IKEA instruction set and using this, which is our 1 to 10 model. with piece coding and post-it notes for the pieces we couldn't see. Constructed, delivered on time, became a big hit. It was really popular. It was supposed to be there for 3 months, ended up being 6 months, then it ended up being 9 months. Kept extending the permit until they were no longer allowed to extend the permit. It's won a few awards. This is a slide from the night before the opening day. So this is about 2 a.m. opening night, or night before the opening day. And what you don't see in this photo is, you see the construction fence outside, but you don't see the 2 steel props in the middle here. And what you also don't see is myself and Alvin and Hanif Kara, our structural engineer, arguing. And we were arguing that we're done. He was arguing that you might have finished, but I'm not signing off on this and allowing people inside, and you're not taking those 2 steel props out. Because the site was never level, and it took a lot of precision to produce this set of profiles. And over the course of the construction, because the site was not level, some of the pieces had to be forced in, some of the pieces had to be cut a little bit more. There was a lot of forcing. And in the end, we learned a lot about zero tolerance on the screen versus lots of real-world tolerance that we had to deal with. We argued that we had a team of 20 students climbing on this thing like monkeys for 2 weeks, and we were positive it was going to stand. Hanif didn't think that our optimism was worth his structural license. So he opted to say that we would open for the opening day with the 2 steel props, open the fence, have the opening. After the opening, we would close the fence, remove the 2 steel props, and do a digital scan for 1 week. Every day for 1 week, we would scan and measure for creep. After 1 week, we decided that there was an allowable amount of creep and we can open the pavilion to the public. But we did need one small caveat, which is we had to put up the sign. In London, this is enough to say, if you fall, it's your fault. That would not work here. So that inspired another project which we worked on. Another project which we're looking at the kind of translation of 2D to 3D through digital kind of layered, contoured means. And this is a project we did for a private client in, oh I forgot, I have sound. I don't know if there's speakers that can plug up over there, but forget it. Anyways, this is a home office for a private banker, a private investment banker in London. And he wanted a kind of sculptural piece that would be inside of his home office and would enclose and disguise all of the different things that he wanted to have in his house. And he's an art collector, so he wanted something that was a hybrid between art, an art installation, and a piece of furniture. And so we had a lot of objectives in terms of trying to capitalize on natural daylighting, maximize the amount of space, blur the boundary between furniture and architecture, and also budget. Budget was a really big issue here. And basically, we thought about it, and at first we were looking at kind of thermal-forming Korean, and we're doing formed composites, and basically everything that we wanted to do meant you had to make it 3 times. You had to make the positive mold, you had to make the negative mold, then you had to make the piece itself. And we thought, okay, well, if you make it once, you just mill the whole thing from solid, but then from solid, it's a huge, huge kind of undertaking. And so just to save on a little bit of cost, we kind of distributed it into a spaced set of profiles, all hung on Z-clips, prefabricated in a series of modules, nested onto a series of flat sheets, and getting as much material efficiency as we could, and then also producing a kind of surface volume and expression that we were hoping for, but also giving us opportunities to do little neat things like have the paper shredder feed through the slots of the paper, through the slots of the wood, and have some of the filing elements actually slide through the slots as well. And so as you can see, it's kind of contoured up above, and then as it goes towards the work surface, it becomes a kind of continuous solid element. Here's the completed workspace, all manufactured and assembled in, it was manufacturing took about 2 weeks, assembly literally took 2 days. In and out, everything prefabricated off-site, went to site, hang the Z channels, come in and just put everything up. That was about it. This process also inspired another project where after that we thought, okay, that's really interesting. We got 75% efficiency, material efficiency with something where we started with a form and then figured out how to build it. But if we say, okay, that's the way we're going to build it, how do we begin designing around that to try to get the most material efficiency? And we say the geometry is actually driven by the way we want to manufacture. So this is a table. It was produced for the Beijing Architectural Biennale. Unfortunately, it was not very pretty when they finished manufacturing it, so we decided to pull it. So I'm only going to show you the renderings, not the photographs. And so it was never installed, or never exhibited. We manufacture. This is one of the difficulties with being over here and also working with Chinese manufacturers. We were over here, we didn't have a lot of exchange with the manufacturer. When they produced it, showed us the pictures, and the exhibition was about to happen, and we decided to pull the plug on it. But essentially it's a table that's driven by nested entities. So all of the geometries that are here is a series of nested volumes, all driven by a series of contours, vertical slices, all driven by a fully parametric model, which allows us to kind of manipulate the spread of the legs, the angle of the torque, the number of sheets you're going to use, and say that you are moving from, we were hoping for 100% material efficiency. We ended up with something like 85, 90%. Like you can see here, there's some sheets that you lose some material on. But in any case, what we're trying to do is say, okay, if we take the material process and fabrication process as the starting point, how do we design geometry around that? So you can see here with the table, you get these kind of voids that look into the table and the glass top over that. Looking at saying that the starting point is the fabrication process. This is a chair which we also did very recently for the Acadia conference, done with Stratasys, where Stratasys has a multi-material 3D printer. And this multi-material 3D printer basically allows you to print something like this, which would be a strip of one continuous surface, where on one end it is, say, cyan, the other end blue. On this end, fully or translucent, this paste opaque, and on this end, soft like chewing gum, and this end rigid like a rock. So it's a very, very interesting process. This 3D printer has two heads. Each head has 96 nozzles, prints at layers of 16 micron. And so by combining the two heads, you can do a matrix of the different materials and produce material gradients. So we basically produced a chair which gradiates from being soft at the places where you touch it to rigid at the places where it touches the ground. And the intent here was, because we're working with Stratasys, we wanted to do a chair that could only be manufactured by 3D printing. So part of the process was to actually just say, okay, let's make this chair as complex as a form, as a sort of highly dense packed mesh, that the only possible way of manufacturing this would be by 3D printing. So we're now working on actually kind of redesigning the chair. Right now, you can see here with the chair, this is the half-scale prototype. It was at Acadia. It was all driven with a process which actually had to build the chair, but also build the support structure. And then afterwards, you have to bathe it in a bath and remove the support structure. So we're now working on redesigning the chair so that it can be built with zero support structure. So that if you understand, what we're looking is analyzing the geometric constraints of how much you can cantilever. So there's different angles that you can cantilever out and different lengths that you can cantilever before the material will start to drop. That you can produce a sort of dense mesh without support structure. So which is what we're beginning to look at now. So the other sort of topic, another one of the topics is performative patterning, which I really like Bridget Riley. I don't know if you guys are familiar with Bridget Riley's painting. She's a British artist from the 60s and 70s, all two-dimensional paintings. But when I talk about performative patterning, I'm not talking about performance in terms of structure. I'm not talking about performance in terms of environment, although those things do take a place in this. I'm talking about dynamic perception, responsiveness, and visual engagement. So actually thinking about a pattern that performs, like it does more or appears to do more than what it actually is, right? So it appears like it's moving. This is a facade which we completed for a shopping center in Thailand. It is on a site sitting adjacent to a freeway. We are not responsible for the architecture, so only doing the facade. Basically, we're looking at a sort of a diagrid which sits along the freeway and creates what we want to call a forced moire pattern. So we're very interested in this kind of moire pattern and interaction with how people move past something and get intrigued by what they move past and want to find out more. So what we take is the diagrid and then have a sort of shifting series of radii. And that shifting series of radii begins to kind of shift the relationship of what we have here as pink cells versus white cells. And you start to get this kind of shifting condition where the kind of relationship between pink and white shifts. And there's times when the facade is more white than pink, times when it's more red than it is white, and more opaque and more transparent based off of the angle that you're viewing at. And you get this kind of dynamic condition of what you're looking at. So all of this was done in an entirely free-form manner, as you saw from the original diagrams, and then obviously we've got a budget, and it's a real project, and that budget means that we can't have 5,000 unique pieces. So we managed to convert this into exactly 5 prefabricated panels, which are flipped and rotated and mirrored across the site. And the color coding you see here is the flipping and mirroring of those 5 panels. Those 5 panels produce this type of variation. So this is the completed facade. It is all CNC bent, actually CNC milled, but the bending is manual. You CNC mill a series of wood jigs and then bend the aluminum around the jigs. Assemble prefabricated parts, taken to the site and delivered. Definitely we did not design the landscaping or teacups, but we did do the facade. It's all backlit with a series of phase-changing LEDs, which kind of help shift that dynamic pattern. This is another project which we're currently working on right now. We just won this competition last year. It is for a public art installation here in South Central Los Angeles. It is at the Metro Silver Line station off the 110. And basically it was for a piece of public arts to decorate this public stair. And what we wanted to look at was the kind of very specific views that happened from that stair. And we wanted to think about it as something where the views, much like the views that we were talking about previously, shift. And as you move up and down and around, like you drive past this there's thousands of people driving past it on the freeway, hundreds of people driving past it on the street, and hundreds of people every day which are walking down the stair on their daily commute. And so we wanted to think about something that kind of framed a kind of field condition of views and produced this kind of moire effect as you moved around it. And so we began looking at how you could take a simple system. It was a very low budget project of taking a aluminum panel, a single aluminum panel, and folding it at different degrees to create rotations. So everything's actually cut identical, but folded into different steps, and each fold gives a different color. In the end, we've rationalized this down to exactly 6 panels. There's exactly 6 panels, exactly 6 colors, and 6 rotations. But with those 6 and different rotations of how they get assembled, we're able to produce a kind of field condition. These are all assembled against a steel frame. That steel frame is then assembled as a veil over the stair. And what you see here is a video which basically looks at our rationalization process. This is basically us working in Grasshopper. This is actually directly connected to an Excel file which has all of the costings from our fabrication guy who said, okay, this is if we do double-sided. This is if we do single-sided color. This is if we do 5 colors. This is if we do 3 colors. This is if we do 5 different panels. This is if we do 2 different, and so we're doing this, and as you can see, all of these options, what you don't see here is equate to a dollar sum. So we're actually trying to get the most variation we can for the least amount of money we can, where there's also a certain point where you actually realize you're paying for more, but you don't see the difference, right? There's a certain threshold where it's like, okay, variation is already enough, it's kind of plateaued, and you can keep paying for more variation, but you don't get return on that payment. And so this is where we're at now, exactly 6 different colors. You can see in this animation here that as you move up, it basically kind of produces this kind of shifting condition that as you move around the stair, it's kind of a constantly shifting thing. Hit a little bit of a home run in the presentation of this one, which was unintentional. Arrived at the competition presentation and was about to get ready to present, and I saw the panel, and the panel was entire community, all people from the community, and there was like an Asian guy, a Mexican guy, a black guy, a gay black woman. Like it was like literally like everything across the board. And as I was talking, I started talking about this as a project, which wasn't just about kind of views, but I talked about it as community, and talked about community as kind of coherent collective of things of different colors and different orientations that come together to become one coherent piece. And that went really, really well. And I was very proud of myself. I walked out of that and I was like, oh, I pulled that one out of my ass. And we won the competition. So as you can see here, you get these kind of varied views from the inside and these kind of different colors. With the prices that we're at right now, we're able to afford doing the different colors on both sides. So you will also have a shift as you move around from one side to the other. And the colors are all based off of LA sunsets, so we're trying to kind of match the LA sunset. The other topic we like to talk about, and this one is probably the most common one in every project we do, and it's about geometric logic, and really think about geometry that's not defined by dimensions, but rather geometry that's defined by relationships. We work a lot with Asian projects, and projects where we're not able to deliver beyond design development. So in the end, we have to hand over a set of drawings that somebody else is going to do construction drawings on. So a very big thing for us is not to dimension. We try to dimension as little as possible. Instead, we try to dimension by relationship. So if we are able to say that something is divide, divide, equal, 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 align, 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 tangent, 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 all of these things which are about relationships, it means that if they have to move something, they don't go, okay, it was 35, 35, 35, we've moved this one 10, so now we get 35, 35, 25. They just don't know it's equal, equal, equal. So that's something that we begin looking at, not only in terms of how we work internally with Grasshopper and begin thinking about these projects, but also how we express things to our collaborators. So this is a project which we recently completed in Bangkok. It is on Planchet Road. This is the site right here. That's actually the site. This is what Planchet Road looks like at night. This is the project that our project is an extension to. It is a 6 million square foot mall, shopping center, third largest mall in the world, designed by Altoon Porter. I just recently found out that Ronald Altoon is very upset with me because apparently I was supposed to call him and ask for permission to do the extension to his project. I didn't know this code, this architect's code, so something to think about if you ever do an extension to somebody else's project. You're supposed to call and ask for permission. Very, very active site, as you saw. Site sits here, has this office tower here, and the shopping center here, directly behind it. Those 3 main axes of connection, which produce those sort of 2 nodes of interaction. What we wanted to do was think about those nodes less as sort of nodes and more as a void between kind of shifted elements, and beginning to think about how we shift elements to create those sort of conditions in the middle, as opposed to thinking of them as an axial moment with a hole carved into it. And by working this way, we were actually able to sit down and fine-tune the model real time with the client and actually talk about their usable square footage versus their kind of efficiency of their footprint, and tweak the model and adjust the model so they can actually sign off with us while we're tweaking things. In the end, we ended up with this. So we have this kind of volume, and then we're looking at the kind of movements of traffic along Planchette Road, mapping those along, and using those as a way of kind of carving and articulating these movements, and those movements get expressed as these kind of what we call these fleshy bits, which we like to think about like the flesh on your fingers here, and those fleshy bits get expressed in a slightly different manner. In this case, it's wood. Where the interiors we wanted to feel very warm, the exteriors we wanted to feel very cold and kind of picking up the intensity of the street. So the exterior skin picks up the kind of pulses of street traffic that are happening here, while the interior gets this kind of CNC milled wood treatment, which we wanted to be a much warmer but still contemporary aesthetic. So you can see here the kind of pulses that show up in the perforated panels of the aluminum, and then the CNC milled interior roof soffits, and then the kind of soffits here. This is the enclosed atrium, and then this is the open air atrium. Open air because what you see here is a set of cables. This cables actually has a series of retractable fabric roof elements, and so this is able to be basically in Thailand you don't have winter versus summer, you have dry versus wet, and in the wet seasons you pull that shut. In the dry seasons, you leave it open. Here you can see some of the details. Here you see some of the kind of fleshy wood, as I talked about before, that articulates where the interface between inside and outside occurs. And you can see here the kind of CNC milled roof soffits, which basically very much inspired by some of the work we did earlier and showed earlier. This is a project which we recently did for the Guggenheim Helsinki competition. It's something that I don't know if anybody here did it. The most populated competition in the history of the world. I think there was 1,715 entries into this competition. Office US just did an analysis of that and said that if each entry was done by an actual office with a principal and 2 architects and 2 interns working on it for 1 month, Guggenheim just got 15 million euros of free labor. So I made a little contribution to that free labor. These are our competition boards, and basically we wanted to think of this waterfront site. We wanted to think of this waterfront site as a sort of vortex that was kind of collecting circulations and emitting views. And so basically you have sort of 3 axis points that enter the site, get torqued, and then leave the project as a set of kind of viewing decks at the top. And those things also create this kind of racking structural system, or reciprocal structural system, where we have 3 separate leaning concrete cores which rotate around the central atrium, and kind of like those tables you see that kind of rotate around each other and lean, the table legs lean on one another, and create this kind of torqued central space, and then creates a cantilevered structure where the entire museum sits at the upper level, and the lower ground kind of cantilevers out over the site. And then the roof skin begins to kind of flare open towards wherever you have north-facing orientation. So those kind of fins start to close off as you move towards south-facing, and so you get a lot of trying to capitalize on the amount of natural light that we can get for this museum, both through the central atrium as a way of kind of bouncing light down through the middle, and then through these roof lights to get it into the gallery spaces. And then looking at the structure and the kind of pattern of the skin, exterior skin, as a reference towards a traditional Finnish sweater, right? And thinking about this kind of snowflake pattern and using that as a way of kind of articulating this fiber-reinforced concrete skin, and environmental diagrams. And this is a view of the project sitting on the site. You can see the kind of central atrium here, the kind of 3 axes coming torquing into the site. The lifted condition of how it moves up, and the kind of view in. One of the things that has happened with this project is they wanted you to use finished wood as a big feature. So we proposed, we worked with Arab on this proposal and basically looked at producing permanent formwork out of finished wood that was able to do kind of all of these developable surfaces as concrete, basically looking at the lower bowl of the building as a series of cast-in-place bowls that were produced by a series of permanent formwork. So after you basically are propping the formwork into place, pouring the concrete in, and then removing the props, and leaving the finish as the formwork. And then on the inside, you would have the concrete. Some of the internal spaces, you can kind of see the tessellated finish pattern there, the interior of the formwork, and then the skylights above, and then the kind of warped atrium space where you've got those kind of stairs all warping around those leaning cores. This is a project which is inspired by Claude Brent and Paul Virilio. Basically, they wrote this treatise called Architecture of the Oblique, which looked at kind of continuous surfaces that would fold to bring people up sectionally through space. Moved through this one relatively quickly and basically began looking at a kind of continuous surface of a mesh that gets relaxed in Grasshopper to produce this continuously walkable surface, where that continuously walkable surface allows us to create rooms and floors that don't have divisions of levels. It's just one continuously open floor space, which as a library we were interested in because as a library you don't have things like divisions between all of your Dewey Decimal systems. It's just a continuous slope that works all the way through. But what we also looked at was with sort of contemporary library, we wanted to produce something that was much more digital, but also looked at fewer books. And so we looked at a fewer number of books that we were able to store in all of the furniture we wanted to look at here as something that was coming from the geometry. So based off of the slope of the climb, some of it was ramp, some of it was stairs, some of it was bookcase, some of it was desk. All of those collectively together starts to give us a sort of inhabitable landscape. Final topic, informed form. Very, very interested in the relationship between form, force, material. Very, very inspired by Fry Otto and his work with form finding, in this case looking at soap film working against a aluminum frame. That aluminum frame holds an edge. The soap film minimizes against that edge. What results is called a minimal surface. A minimal surface is a surface with zero mean curvature. It's something that is very difficult to figure out intuitively, very, very easy to figure out with physics. Now with computation, you can actually figure it out on the computer. So we're working with Kangaroo for Grasshopper, which I'm sure some of you guys are working with, and looking at how you can do catenary curves, catenary meshes, inflatables, tensile fabrics, and in our case, looking at kind of the minimizing of a soap film against a frame. So we began this study by beginning with known variations of minimal surfaces. All of these known versions have specific equations that are tied to them, and those equations and produce very specific forms, and there's all of these different catalogs. And we began looking at how you could reverse engineer those as a series of low poly meshes, and then through that, minimizing that low poly mesh, produce the actual minimal surface. This was done through a project at University of Calgary, a workshop I taught there. This was a workshop where we began looking at this to produce an installation, all CNC milled acrylic, and put together as a series of rigid panels. We basically reversed the forces on the tensioned mesh and think of it as a rigid shell structure. That inspired this, which was a pavilion for a festival in Canada, which was again looking at that same rigid shell structure. The funding for this pavilion got canceled because of the floods in Calgary, so we lost all our funding for that. We were looking at using Karamba, which is another structural solver in Kangaroo, or in Grasshopper. And what that does is it looks at the principal stress lines in the shell. The principal stress lines are opposing, so you have blue in one direction, black in the other. Essentially what that tells you is one direction is where you have zero mean tension, the other is where you have zero mean compression. So every material, when you analyze a certain slice of it at any depth, will give you a zero mean tension and a zero mean compression. And when you connect all of those lines in a mesh, it produces principal stress lines, and that's what you get here and here. So what those tell you is actually where you want to have the most material and where you want to have the least material. And so we began looking at how we can map those against that mesh and begin kind of tessellating the mesh in different ways where the mesh becomes the most porous where it doesn't need material and the most opaque where it needs the most material. All of that ends up in this, which is a pavilion we did for Volvo. It was a result of a competition for this, which is the Volvo V60 plug-in hybrid electric diesel car. Not available in the US. There was 200-something submissions to the competition. All of the finalists and all of the submissions is that most everybody thought of the competition for a portable structure to showcase the new car as a prefabricated garage. And the way you think of a garage is it's a destination. The car drives to the garage. We wanted to think of the pavilion as something like a backpack or a tent, an accessory, so something that you bring with the car. So the two parameters we gave ourselves at the start of this project was to say, okay, one, it's an electric car. We want the pavilion to charge the car. Two, the car is mobile and we're interested in fabrics. So we want to design something that can fold up and fit inside the trunk of the car. So what we designed is a form-found fabric structure which flat packs, fits inside the trunk of the car. And I won't show you the video because it's a lot of talking and stuff that you won't hear, so I can just kind of walk you through it. So what we started with is a geometric pattern which is designed around the notion of three. So there's 3 points on the ground, 3 points in the air. Those 3 points represent the 3 modes of the car, which is power, hybrid, and electric. Produces a hyperbolic surface like this. And then to keep when you do that surface, those 3 points that are up actually want to fall out. So to keep them from falling out, we actually add these eyelets here. And those eyelets tension the thing together. And so what we're looking at is a frame condition as an aluminum frame that is pre-tensioned and basically wants to push out, and then a fabric system that is pulling that back in. So the equilibrium between one frame wanting to push out and the fabric wanting to pull in actually creates what's called a bending active structure with, when it gets to zero equilibrium, means it's a stable structure. These are some of the early study models we were looking at for the geometry. At first we were looking at how you could actually create multiples, and so if you created a sort of nesting geometry, you could create lots of them and assemble them together to create a kind of city of pavilions. We were working with Bureau Happold for the structural analysis. We were working in both Karamba and Rhino, but also working simultaneously through hand models to kind of test our intuition and try to understand the physics of it. Bureau Happold is working with a structural solver called FEM Membrane. Our Kangaroo software is free. Theirs is $45,000 a license. We spent a lot of time on ours. They spent a lot of time on theirs. We had to figure out how to rationalize the freeform geometry of the perimeter. So when we first got the quote for CNC bending, I'd never done CNC bending before. When we first got the quote to CNC bend the perimeter, it was exorbitant, like way out of our budget, and I couldn't believe how much it cost. And I called the guy and I said, why is this so expensive? Just go tell me how the pricing works. Explain to me. And he said basically they take freeform geometry and they turn your freeform arcs, or your freeform curves, into a series of arcs. And ours had something in the order of 2,000 arcs to get that freeform geometry. And I was like, so if I can turn it into 5 arcs, how much is it going to cost? And it was really, really cheap. So we managed to get it into 5 arcs. Re-rationalize the entire process against those 5 arcs. So it basically, once you have the 5 arcs, you re-tension and re-minimize the mesh against the new arcs. redid the structural analysis. This is the structural analysis done by Bureau Happold. Our geometry was done in Kangaroo. Theirs in Rhino, or in Membrane. We had a 2% differential between our form findings and theirs. So I was very pleased with how accurate ours was. But again, that 2% is the difference between us getting sued. So I'm very happy to use their geometry. We also had, at the time of the competition, a series of flexible solar voltaics pasted to the skin, which we put in a more graphic pattern. We didn't really have an idea. It was just purely aesthetic. We then, after we won the competition, we knew that the pavilion was going to travel, it was going to go around Italy. It was going to be put in lots of different places, lots of different orientations. And so what we did is we analyzed the pavilion for 365 days of the year in 360 degrees of rotation for 8 hours of the day, and found zero mean solar incidence, or not zero, highest solar incidence for the skin on each of those conditions, and averaged them out into a gradient map. Use that to map the presence of the solar panels. It actually scales according to the gradient. All of that is then fed back into the grasshopper, rationalized into developable strips. Those developable strips are unrolled and then taken into cutting. It's all manufactured. The other thing we have is solar arrays are only as powerful as their weakest link, which means that at this case, these are the only ones that are useful. The rest are actually not producing anything. So what we have is this thing, which is called maximum power point transmission controller. And what that does is it real-time senses what all of the panels are pulling in. And as it's pulling them in, it says, you assign a threshold and say, I want minimum this much power, and turn everything else off. So what you see in this diagram is basically which panels are working, which means that all time we're getting the minimum threshold of power that we need to the pavilion. So everything is CNC cut on a zoomed as fabric stitched together, laid out this way, taken to the site, CNC bent here, assembled in exactly 24 3-foot long aluminum pipes, which are swaged and have a slip fit condition. Assemble like this. This was our first assembly. It took me and these two gentlemen in our first assembly of it ever 45 minutes to put the whole thing together. With a more experienced crew, we're getting it down to like 30 minutes. It still has it's still more than we want it to be, and right now it still takes more than 2 people. It also takes a very large ladder. So what you see here is at the kind of prototyping stage, and then we were not able, in the end, to get the wiring integrated into the seams. Since then, we have now gotten the wiring integrated with the seams. We're now working with Volvo to develop this as a commercial product. So the wiring will be integrated in the seams. We also, at that time, had to buy off-the-shelf PVs, which come in a set dimension. We've now developed a process with our manufacturers, which we are able to CNC custom shapes of PVs. So now the PVs will actually be the shape that we're producing. This is the finished pavilion. I'm going to end with this slide. It's the same slide I always end with. The first lecture I ever gave was at a conference called Digital Architecture in London in 2009. And I ended with this quote from Mark Weisler, who is the godfather of ubiquitous computing. And I think one of the things in terms of thinking about architecture is that it's always been inspired by and informed by and driven by advances in technology. And I don't think there was ever a time when Mies was talking about the fact that he did rotring architecture and or parallel bar architecture. And I don't think we should be thinking about what we're working on now as digital architecture. It's just architecture. Thank you. That's the image of the car is at that time called a horseless carriage. Flash forward 100 years later, nobody remembers the horse. It's just a car. So right now we're talking about digital architecture. 20 years later, we're not going to remember digital. It's just architecture.
If anybody has a couple, we can probably take a couple questions from the audience. No questions? Oh, speechless. You've left them speechless. If we can thank Alvin one more time for coming, I really appreciate
it. Last quarter, and they have a set of skills that I think are sometimes way better than ours at certain things, and you start enriching the way you learn and the way you produce your work because you start seeing the value of speed and different skills you can gain from there. Just really quickly on price, I spent, I think on the individual level, just on the base rate, it's around $8,000. I spent around 10, but like I said, there's so many things. No, I must say, I am a spender, and that's why it was really bad. Don't take a lot of things because you will shop. You'll find a lot of things that are really inexpensive, things that you don't find anywhere else in the world, and you definitely want to bring them back. So, but yeah, it's a really fun program.
So in the China program, you can actually get ahead in your studies because you're doing it over the summer. So this is a really great program again for for third years who want to study abroad but don't want to fall behind, and then also you come back and you can get credit for Topic Studio during 5th year. So then you're actually ahead in this program, so you can have more time to work here, more time to focus on your senior project. Yes, is there a question?
You can study, you can do the China program over the summer before you do a year abroad?
Yes, you can. However, there are some limitations as to how much credit you can get. But we do have students that have done both the summer program and then another program after, whether it is the a year program. Last year, we actually had a student who did China in the summer, and then